Hello, I'm Bradley Sward, Associate Professor of Computer Information Systems at the College of DuPage in Glen Ellen, Illinois. And this video is going to take a continued look into object-oriented programming. So I presume you've watched the video before this one when it comes to encapsulation and data hiding and just setting up the basics of object-oriented programming. We're going to have a quick review right now, but I'm presuming that you at least have those understandings before I push forward here. And in this video, we're going to look at static member variables, we're going to look at constructors, copy assignment operators, operator overloading, all those kind of things. The next video, not this video, will look into polymorphism, inheritance, virtual functions, all the the big stuff, all the big 4 or 5 syllable words to finish up the discussion about object-oriented programming. So when it comes down to it here is our review of everything I wanted to talk about here. So I set up the .h file, and remember, like many of the students I have already have given me homework assignments with everything just jammed into one file, and that's just not the way things are done. Every class gets its own separate file, the header gets its own file, and we'll show here in a minute the implementation, all of the functionality gets its own file as well. So all I've done pretty much is just filled in the gaps. And so this is kind of, setting up an object, sometimes it's easy and sometimes it's more challenging. And it just comes up to how much have I thought through, how much do I know about what I'm trying to solve at a given time. And if I just tell you up front, I want a circle that has an X position, a Y position in space, and a radius, well, everything else should kind of come for free as long as nothing later comes down the road and I say, hey, I want to add this, or I want to remove this, or wouldn't it be cool if, those kind of things that designers and developers are keen to do is always advance the code that we currently have. And so here is the private data. Private data usually goes on the bottom because you don't usually need to see it. Usually whoever's using your code wants to see your public API. They don't want to see all the stuff that's going on under the hood. They can access it if they need to, if they have access to the source code. But all I care about is the public interface. So I have my constructor that sets up all 3 of these elements. I have get and set functions for each of the 3 elements here, all the 3 member variables. And remember, you don't have to grant access to these things if you don't want to. And so we'll see in the future where, there'll be plenty of times where I don't want you to access things that are sitting under the hood. Those are private to me. You shouldn't be able to access that kind of stuff. And so gets and sets and the constructor, that's always basically the first, that's the boilerplate, the tedious, boring stuff that comes along for the ride, just getting things going, setting things up. And then afterwards, you're like, well, what other functionality do I actually need? And so in this case, just to kind of get the conversation going, I have an area function and a perimeter function. You can think of it as circumference, but I'm pushing forward into 2D space and 3D space with this lecture. So it makes sense that there's no such thing as a perimeter in 3D space. I don't think anyway. It's more of a, perimeter is more of a 2-dimensional idea. And so just the kind of surface area, or this is surface area versus area. It's just terminology, and so we're just going to try this example out with circle versus sphere versus cylinder as we push forward today. Okay, so implementing these things, if you want to type them all out, you can, but you can go ahead and do this kind of stuff to get things going and set up that CPP file automatically. Who doesn't want automation in our lives, right? So that set up all of these files, and now I don't need this Solution Explorer anymore for a little bit, so I can go ahead and kind of break things up. And so now here are all the functions, and they're no longer green because I've defined them over here, so I can find them. And now I just have to fill in the gaps. So if I'm going to get X, I'm going to return my X. If I'm going to get Y, oops, sorry, everything's a weird, that's odd. I didn't do it. Hold on, get X, return X, get area, we'll fix that up. Set, oh my goodness, what kind of order are these things? I've never seen it like that. Okay, set X, lowercase y equals uppercase Y. Get X, return lowercase y. Set X, lowercase x equals uppercase X. And so remember, this is a big deal when it comes to programming here with object-oriented programming, is that you have this lowercase y, and we just, where does that come from? It comes from the fact that it's part of the class, and you have public access, or I guess private access, but you have access to everything stored inside of here. You can access this as if it's your own stuff because it's private to you. So public can only be accessed outside of the class, But anything public, protected, or private can be accessed by you inside of here, even though it's not explicitly defined inside of the function call. And so lowercase y equals uppercase. This is get perimeter, get area, set radius. Radius lowercase equals radius uppercase. Get, set. I am missing something, aren't I? Oh, how is this even compiling? You do your best and you screw everything up, right? That's why it's not coming up, right? So let's see. So I got get x, set radius. Oh, jeez, we're 5 minutes into the video. I don't want to start over. Okay, so get y, set y. This is, so I have a set radius, so I'll just steal the get radius here. Automation lets you down sometimes, because I thought it would at least tell you, I can't do this because you're duplicating what you're doing here. So get x, set x, let's group these things together a little better real quick. Show you that I'm not, if you need any more evidence that I'm not perfect. Get y, set y. Here's the get and set for x. Here's the get and set for y. Here's the set radius and, all right. And here's the get radius. Back in the old days, I did this by hand, and that was the way I liked it. Okay. Didn't like it that way. Get radius, const. Oh, and that's another little thing here is that when my function is not going to modify any of the data stored inside of the object, I throw a const on it just as a reminder that it's not going to happen. And this makes it easier for operator overloading and the standard template library, because the standard template library has a lot of const issues that do come up occasionally if you're not paying attention to things. So if you follow best practices, anything that's a get should have a const, and I'll fix them up on both ends here. So I didn't do it perfect by any means, but now it's there. And so now I'll fill these in a minute here. And so now the constructor is the last big deal. And so the contract you have is that when the constructor ends, that the function, all the member variables inside of the object will be initialized to something valid. And that goes with an initializer list. Lowercase x gets uppercase, lowercase uppercase, lowercase uppercase. And that's across the board. And it's surprising that nothing goes here. Eventually we put stuff here. We'll put stuff here in a little bit, actually, when we start talking about 14.1 here. And so all of these, and say, once I start adding and removing and changing things, if I screw up and forget, I'll never see a compiler warning, I'll never see a compiler error telling me that I'm leaving something uninitialized. So in C++, at least, you have to be very careful that you're not leaving things to chance and leaving things as garbage, in a garbage state. But again, that's your contract. Every variable needs to be put into some value. And you don't always need a 1-to-1 ratio with parameters and member variables. We'll see that later on. If not today, then in another video. Okay, so then we say we got all this cool stuff. So get area, pi r squared. So 3.1415926. 535. Oh man, I know the last three numbers, but I don't remember them. But pi times radius, times radius times radius. That gets me an area, and then perimeter is 2 times pi 3.1415926.535 times radius. Pi times diameter, right? Pi times 2 times radius. So there we go there, and so we're good to go. We have now implemented both sides of this thing. We've both implemented the header and we've implemented the actual implementation. And so now we're ready to kind of push forward and continue on. I'm not going to create anything. We'll have time later to create everything and use it inside main. But this is pretty much everything I need to do to get going now. In previous lectures or previous classes, you should definitely have been made aware of what a static variable is. And so a static variable can give a function memory, because basically only inside of that function can you access this variable, but this variable stays alive. It's scoped throughout the entire program. So say like just to say we can do that sort of thing where we could keep track of a member variable, a static variable, and keep track of how many times I access the specific function. Or in this case, it'd be kind of cool if I could access how many circle objects are in scope at the current time. And so they say a normal member variable is what you see here. Everybody gets their own copy of every member variable. So if I set up 10 circles, I get 10 x's, 10 y's, and 10 radiuses, one each for each of the 10 circle objects. But it's a little different on the side of the static variable, at least when it comes to the static member variable. That one variable is shared across every object of that class type. And so it's a completely different way of thinking about it. Everybody's sharing that one member variable. And the only way I can think of wanting to do that would be to keep track of like an instance counter, at least for a simple example for you guys. So a static variable is one variable that's shared among all objects of a class. And again, it's a little different than a member or a static variable in a function, which is just shared inside of the function itself, but you can use it and you can maintain it for the entire lifetime of your program. And so if we wanted to set up this counter, I can go ahead and do that here and say, okay, I have a static variable called int, and I'll call it count. And that changes, and as you can imagine, this changes the way I define it. This changes the way I use it. There's a lot of little rules here. And so the rules kind of change here. But I can't go ahead here and just go, I'll just put count. And I'll put a 0 here. It doesn't work like that. See, it automatically blows up. And it says count is a non-static data member or base class, blah, 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 blah. And so you actually define static variables outside of everything. So the syntax is a little weird. It's kind of like what you see here for the member functions, but it's the same kind of deal, where I say, okay, int is my data type. You don't use static anywhere here. And you say circle, oops, I just got to spell it right, circle, colon, count equals 0. And so this is static, and a static variable is initialized prior to the main even running its first line. So the lifetime of this, as far as we're concerned, the lifetime of a static variable or a static function or static anything is the lifetime of the entire program. So this thing is set to 0 before main ever runs, so we can presume it's going to be in a valid 0 state before we get going. And so that's why it has to be placed outside of everything else. The compiler finds this somewhere in here and it knows to set up that static variable ahead of time. And so, try this. This will build now, of course. Uh-oh, what did I do wrong here? Oh, the comma here. Okay. And so now you can see that agrees with what we have here when it comes to static int object count. And then they're going to, and the way they defined it, they defined it in the same file, but we defined it in the same way outside of the class header itself. Int tree : object count equals 0. Okay. And let's see. And then right now there is no static member function to use this thing. And so where is it? So here we go. So we'll need a static function. Static variables need static functions in order to access them outside of the class themselves. Because I should be able to access since this thing is a global variable essentially, I should be able to access and ask how many objects of circle exist even without a circle existing at all. And I should be able to go in and access that variable. And to make that happen, it has to be a static function on the other end. And I could say get count. And it can be a const. And so static comes first, then the return type, then the constant. Oh, I'm sorry, const can't be part of the static function. Forgot about that. And so I can define this thing, oops, quick actions and refactoring, define this thing in circle CPP. Where did it go? Down here. And I can just return count, just like I can do any other. It's just I got to throw the word static in front of it. So let's see. So to access a static variable, I have to be either inside the class with an object, or I have to have a static function to access it. I cannot access a normal member variable without having an object. So I can't call and have a static function that gets me member variables, because again, remember, when I'm basically going into a static function, I'm kind of going outside of the realm of being a member. I'm kind of just a visitor in a way. And so there is no, so I'm kind of looking over everything, but I don't get to see the landscape of any particular object. I only get to see the stuff that everybody shares. And most times that's nothing. Almost always you're not sharing anything because you're not using anything static. And that's why you hardly ever see what we're going to do here. But now we can do this and say, okay, for count we can do this, where we can say, okay, get me the count, and the syntax is going to be completely different how we access this. We can access this variable as well. So let's go ahead and work this thing up a little bit real quick. So I'll just include a circle. Remember, the stuff we create gets quotation marks as opposed to angle brackets for all the general C++ libraries. And so I can create a circle, and I can create a circle C, and I'm just going to put the same variables in. This isn't part of anything I'm worried about here. But now I'm saying, like, how would I access this static variable that I just defined? So you think you can do c.count, and notice again, there's nothing here. It's private, but there's a getCount function. And I can do this. I can call a static function from a non-static function, but I can't come the other way around. I can't just say, hey, circle, get count. I can't. How would I do that? There's no object where the cursor is right now. And so what I can do, though, instead, for a circle, to do that, I can say, hey, circle, get me your count. And notice the syntax is completely different than c.getCount. Again, because I have an object, I can get count this way. But if I don't have an object, I can get it through globally asking, or not globally, but I guess asking through the circle interface, the circle namespace, the class definition. So you better believe this will print out a 0, right? And then, if I do this a second time, oops, I'll need a std::. And so you better believe here that if I do this 2 times, it'll be 0, then it'll be 1. But, except for it gave 0 both times because we didn't actually go in and change anything, right? We have zeros. We have 0 and 0 for the get count. Fooled you, right? I fooled myself too, and I've just completely blanked on doing that. But what I need to do here, I need to access and fix up my code so that the count increases when I instantiate an object and I create one, and then I subtract one when I destroy one. And so to make this work, this is a case where I would need a destructor, because that is the only place that I have to when I destroy an object to fix up other variables in my code. In this case, I need to fix up count so that it's a 0. And so I'll just go ahead and define it here. Hopefully it'll put it right below it. There we go, good. And it really is just a matter of now destroying this nothing here and just saying plus count. And then on the destruction side, say minus count. Every time I create an object and I use the constructor, here you go. I have a new object in my program. But once it gets descoped and the destructor gets hit, well, I'm subtracting off, and it's not working anymore. So now, at least now, you can see no more laughter. Now it's more serious because it started out with 0 in the main, and then it started out with 0, and then after I created it and I get the count there, I can get 1. And so it's hard to show this in main, but if I jam this around, what will happen now here? These curly braces are just there just for show. And so this better be 0, this better be 1, but what is this one going to be, right? That's the big question. You could probably imagine what it's going to be. It's going to be 0, 1, 0. So when I hit these closing curly braces, this circle C gets unscoped. And so the destructor gets hit on circle C, and so when that happens, that object is removed, and the destructor calls and decrements that variable. And so it'll be 0 here, 1 here, and 0 here. You have to watch out for dynamically allocated memory, because remember, until I go and explicitly call delete, that thing exists in my memory in the operating system in the heap. And so unless I explicitly delete it, I might have a memory leak if I forget to go back and delete it later. So you have to watch out. So like if I did circle pointer d equals new circle, the same old nonsense, 1.0, 1.0, 1.0. And so now I try this again, you'll see 0, 2, 1, right? Because even though I nude up everything and you're like, well, this D died and got descoped when I hit this curly brace, I didn't explicitly delete the memory, so it's still sitting in memory and nothing's telling it otherwise. So now there's 2 and now there's 1 because the C gets destroyed but D doesn't. The D variable gets destroyed, but not the memory D is pointing to. So if I don't, so I could bring it back if I just delete D. And there we go, from 0 to 2 to 0, because delete D explicitly deletes the memory pointed to by D, and then the Destructor is implicitly called when the curly braces hit here for C. But that is pretty much it when it comes to static member variables. And so I think we're ready to push it on to friends and classes. Let's see anything else. And so again, just one last time, this is kind of what's going on. That one static variable, every object is pointing to it. So if I affect it, like you're saying, if I affect it one time in one place, it affects everybody. Because we're all sharing that variable, that little piece of paper. Anybody can come along at any time and cross it out and put a number another new value in, and whatever the newest value in there is the one I have to obey. And so it works. I mean, for what you need to do, most times it works. Sometimes it still is a little iffy, but I think we're good to go with that explanation. Let's push forward into some operator overloading and some more constructors and stuff. We will see the idea of friends in a little bit. I don't know of any other language that has this idea of a friend function or just a keyword friend. And it means pretty much what you might think it means, because we have private data, we have protected data once we get to the next chapter, and we have public data. And it just comes down to, can I trust you to go in and look at, basically look at the insides of my object and not screw things up. So like I attribute, or my analogy is, you're going on vacation and you have a dog and you need someone to take care of your dog, and you give your keys to your friend. And you're like, I'm going to be gone. Please take care of my dog. And when you're out, you're gone, you're doing your thing, and you're trusting your friend to go in and not ruin your house, not leave the door open, not let it get robbed, not have a party. You're trusting them to go in, take care of the dog, do whatever they got to do, feed the dog, walk the dog, whatever, and then go back and leave everything exactly the same. And so, or just change exactly what you need to change and nothing more. Because you're a friend, you're not just some random person who goes in and destroys things. And so it's the kind of the same thing here. And so a friend will be a function that allows somebody to, even though they're not publicly accessible, like a member function or a member variable, they can actually go ahead and treat those private functions and protected functions and protected and private variables as if they were public. And so we'll see that when we get to the operator overloads in a little bit. And so it's just one of those things you have to use for some of these operators to overload. You just have to get used to the rules. There's, I think, 3 different ways at least that you have to overload certain operators, and you just have to get the experience. And every so often I screw up, and I've been screwing up everything else. So I might screw that up too, but of course I'll fix it up as I go. So you can have a standalone friend function, but again, a friend pretty much only applies to classes and structures, because it's variables that are sitting inside of a structure or a class. It usually doesn't apply to anything else. So I'm kind of curious where, int_val reference. I guess int_val is a completely different object or something like that. So yes, it makes sense that you're talking object-oriented programming when you're discussing the idea of a friend. And again, you can have friend classes, you can have friend functions, and you can have all sorts of crazy stuff. All right, so moving on here. So let's talk object-oriented programming. Back it again. Okay, I'd like to draw your attention here for a quick moment to this right here, Class A. And so member assignment, all these things we're going to talk about now, we're going to override behavior that is default part of C++, part of a class like this. What member functions or functions of this class come for free if I leave it like this? Because I can go ahead and set up an A, right? I can just say A, capital A, lowercase a, and it's perfectly legitimate, right? But we just told you, don't mind all that extra nonsense here, but we just told you that you have to have a constructor, and you have to have this, and you have to have that. So there's got to be a way for this program to run, correct? So the constructor is one of the functions that comes for free if I go ahead and just set up an object. And so if a constructor comes for free, a destructor comes for free, quote unquote, for free, because it has to be, if it needs to be constructed, when it hits that closing curly brace, it needs to be destroyed. And so there are 3 other functions. One of them is new. By new, I mean at least 9 years old at this point. One we call the copy constructor, which is, if I'm trying to set up an object, this is fun here. You go AA, and then I go AB equals A. And so this uses the copy constructor. And this says, and we'll show this in a little bit, and it says that I'm trying to create a new object on this line of code called B of type A, and then it's going to be equal to everything inside of it is going to be, all the member variables are going to be exactly the same as whatever A is, and lowercase a. And so this is the copy constructor. So just at the end of the day, both of them are going to have the same values. And then it's tricky because there's a difference in C++ between these 2 lines of code. As much as it screams out and go, gosh, this is not right, but it is. And so that's called the copy assignment operator, and that's what member-wise assignment is describing here. Copy assignment operator. So this is essentially equals the equals operator. And so again, all 4 of these. Oh yeah. Then the 5th one is a newer one called the move constructor. Oh, I guess there's a 6th one then. There's a move assignment operator. We won't really talk about this too much in this course. That would, but there are so 6. Okay, so it used to be 4 back in my day. Back when I was going through things, there were 4, and now there are 6. And so yeah, this is kind of not as big of a deal, but it is a big deal because they spent a lot of time and effort creating move constructors and move assignment operators. And so I can use, I can use the equal operator here. And so again, this is completely different stuff. And so they show it here. They show how to set it. No, they don't. But let's go ahead and define this copy. We're going to define, let me get rid of these 2 for now, and we'll define these 4. And so the copy assignment operator, if I needed to go ahead, I guess we could do this for a circle class. We don't have to do this for this stuff. So what we have from class A, let me get rid of all this and bring it back to our circle class. Circle.h here, is we have our constructor. We have we took over the default constructor. We have now a destructor. Again, sometimes you have to take these things over and sometimes you don't. And so part of the experience is knowing when you do and when you don't. And so you can see I don't have the other 2 here just yet. And so I need that copy constructor, and I'll need that copy assignment operator to make this thing work. And so, okay, so to make this thing work, I want to return a circle reference. I want to make this, this is our first time using an operator. You'll see the word equal, and then you'll say on the right-hand side, const circle, never spell circle, right? Circle reference RHS, the right-hand side. And so this defines this operation so that, okay, so this is weird, right? Because you don't, like, how would you define this? This operator equals, the left-hand side is presumed to be me, this. And we'll talk about the this pointer in a little bit too. But so there's 2 operands on both, one on each side of an equals, right? There's the left-hand side and the right-hand side, RHS. And so in this case, using this operator, the left-hand side is presumed to be a circle object. It's just presumed. It's just part of the fun of the syntax of the language. And so we can define this thing for circle class. And so what do we need to do to set 2 things to be equal? Well, we need to set the x, y, and radius to be the same. That is pretty much true. The count is not part of this because just because I'm setting something equal to another thing doesn't mean I'm adding or removing an object from existence. So I've defined it down here most likely. Okay, so it goes exactly like you might think it does. You say lowercase x equals RHS dot x. My x is now equal to the right-hand side's x. Everything moves right to left when it comes to the order of operations in your program. So RHS dot y and radius equals RHS dot radius. And the reason why we have a return here that isn't like a void is so I could chain things together, so I could have A equals B equals C equals D equals E on the same line of code. And you don't want that. You can just get rid of it and just put a void there. But this makes things more flexible for anyone using your code. And you have to return, and like, and that's what I'm saying here. How do I return me? Because I'm the one that needs to get shifted along, because I'm the left-hand side of this equals operation, but as long as I'm moving left to right with this, or right to left with this, I'm going to be the right-hand side in a minute, in the next operation if I'm chaining these things together. And so I return star this. We'll talk about this. We dereference this pointer because under the hood, there needs to be a way for the compiler to reference who am I? What, whose x value, whose y value, whose radius is this? And that is with this idea of a this pointer. And the reason why this is a reference is so that I don't return a copy of this. Because I don't want to because if I keep chaining these things together, I'm making copies. And by passing a reference, I'm passing the real data. And you notice the word const here, the const keeps screaming out, you can't modify this under the hood. So I can keep passing it along, and I can always make it more secure by adding constants to it, but the second I try to remove that constants, that's when everything's going to go wrong. And say, okay, expression must be modifiable L value. So this is a perfectly legitimate way to do this. And now I've defined my own equal operator. So now coming back here, I've defined this, and I could say, so coming back here and just putting in random values here, I can say D equals C. Oops. Because I'm using a pointer. Let me get rid of the pointer notation here. Like, why isn't that working? So now I can say D equals C, and you can see how things go with this equal operator. And you can see that, okay, so at this point, D is 114. And then as soon as I go into this code, you can see I'm changing stuff. All right, here's the right-hand side, which is supposed to be 111. And so X is going to be 1, Y is going to be 1, radius is going to be 1, and there's nothing to change, so this doesn't hurt anybody. And so now coming back, you can see D has now been changed to 111 because everything that's part of C has been now placed into D. And that pretty much covers exactly how to do the copy assignment operator. And again, it's the same idea as the constructor. If I forget or I neglect any of the variables that are supposed to get copied along, there's never going to be a compiler warning. There's never going to be a compiler error. It's just one of those things where it's like, oops, that's what you wanted. C++ just presumes that's exactly what you wanted. And so again, this is weird because this is not the same as what you see here. And I can show that by putting a print statement. And so I can do a cout, and I can put equals, and then I can put an end line here. And I can prove this. Oops, I need to include IOString in here apparently to be able to do this. I have to remember to remove it later when I'm done showing this. And so I can show this for sure by saying circle C equals D. How many times do you think this equal sign should print? You would think it would be twice if I didn't tell you otherwise. And so it'll print one time. And you can see there's the count. Oops, oh my goodness. The count of 0. Oops. The count of 0, the count of 1. Hold on. Jeez Louise. Ay. Fun stuff here. Oh my goodness. What in the... Okay, let me start up. Why can't... What the... Computers are fun. Okay, so... Whatever I just did. Let's start this over. Okay. So there we go. The count is 0, and it only prints the equal sign one time. And it does it for this line 13 right here. So this tells me that it's doing some other code. And that's not this, I say, these are default things. Generally speaking, we do not have to go out of our way to set these things up. That's why they're defaults. It's only when we have custom behavior and custom functionality that we have to worry about. And in most cases, that has to deal with dynamically generated data, like pointers to Nude up memory. And so, saying we don't need this for the circle class, but I'm just showing you how you would implement it if you were implementing exactly what the circle class does under the hood already. So coming back here, so this is perfectly fine. I can get rid of this, and now I've proven to you that member-wise assignment is different than the other copy constructor. Okay, so here is the idea of a copy constructor. So it's the same exact idea, but now it is a true constructor. It's not like it's just a regular function of things. So how do we do this? It's the same idea as what we just did for copy assignment operator. It's just, remember, the rule is the function name is the name of the constructor, no matter what. You could have many, many constructors. And then you just pass a const reference in, and you're doing the exact same work. You're copying all the data from point A to point B, but you're not returning anything, because you can't chain constructors together like you can for the copy assignment operator. So I can basically go ahead, and everything that I do here now, I can borrow this guy, bring it up to the top here for my copy constructor, and say, okay, circle, colon, colon, circle. And now, because it's a constructor, now I can change this up. And I'll put equals equals just for that. That's defining the copy constructor. Single equals is the assignment operator. Double equals is the copy assignment operator. And so there's no return you never return anything from a constructor. And these three variables here are going to be part of the initializer list. X is RHS.X. Y is RHS.Y, and radius is RHS.radius. And otherwise, everything can stay the same, and I want to print the equals, and now you'll see when I run my program again. But before I finish this up, I just want to add a few things, since I screwed it up and I started this video over, that in both cases, both constructors, I'm adding to the count, coming back to our idea of keeping track of how many objects are in scope at a current time. This is a constructor like anything else, and so I can go ahead and do this. And so then I can set that up so I'm using triple equals for just the plain old constructor, I'm using double equals for the copy constructor, and then I'm using single equals for the copy assignment operator. And so now I really can come back in here and try everything out, and you can see that I'll hit all three of these now that I run my code. Because, oops, did I not put after all that, did I not put an end line here? Hold on, put an end line here. After all that, I didn't even test my test case. Okay, so here we go. So I can, coming back to my code now, I can go, okay, I print out 0, but then here's this one. This one is just the normal constructor. But you're like, well, is it? Yeah, it's the normal constructor, because this is setting up using these parameters. It's not a copy constructor, because it's not using a completely different object as it's being constructed. And so then the next one is using the copy constructor, because it's constructing something with something that previously exists. And then this one is both of them exist, so it uses copy assignment operator. So I guess the question, so when like normal constructor, copy assignment operator, you're doing the same operation. You're setting equality, but the question is how many of the objects on the line of code exist at that current moment in time? If the answer is 0 and you're creating 1, then you use the regular constructor. If the answer is 1 and you're creating 1, then the answer is the copy constructor. And if it's 2 and you're not creating anything at all, then it's the copy assignment operator. And so that's the whole idea here. So it's a specialized constructor to use in this case when you're initializing another data's object as your own. And so their examples are pretty terrible when it comes to just the setup here. And so here you say like they do it wrong. We use initializer list. This is C++, not C. And so the copy constructor always takes a reference, a const reference, because you're never going to, when are you going to copy something over and modify it? You're never going to. So you're going to pass along a const reference in the case of the copy constructor and the case of the copy assignment operator. So let's see, anything else to note here? There's a lot of stuff. And now we can get into all the other operators that we need to overload. And we will be overloading quite a few of these things in the next 5, 6, 10 weeks, depending if this is summer or fall for you. And so we're going to be overloading, what are we going to overload first here? We've already overloaded the equal operator. And so you can overload equal, you can overload plus. And so operator overloading, it's a sanity check. Do I need to have a plus for a circle? I don't know. Do I need to have a multiply for a circle? Well, maybe a multiply could change the radius. I'm just spitballing it here. And so you have to think things out. Like, it doesn't make much sense for a video game character like a werewolf. Like, what does werewolf times werewolf mean? It doesn't make any sense at all. So you don't need to define these operators if they make no sense. It's only when, like, a math operation, like if I had like a complex number class and I wanted to add or subtract or multiply or divide, well, yeah, then I want to do that, where I could take an object and multiply by another object and generate code to handle whatever that operation would do under the hood. And so it's, again, sanity check stuff. So we'll just show you, for circle class, there's really not much, but I guess just for the sake of just showing you a few of these things, we could talk about like the multiplication by changing the radius. So if I multiply a circle by by a double value, I will change its radius. I won't change its position in space. Or maybe we could use that for plus and minus, where we can move the thing around. But again, this is just like, does it make sense that I'm doing these things? And that's why some languages like Java don't even allow operator overloading, because it's like, what's the point of this? It's just nonsense. And Python allows it, C# allows it. Some languages do, some languages don't. Some languages have const, some languages don't. Some languages have pointers, some languages don't. So it's just a matter of going ahead and doing things. And you've already done one here, but so now we'll do a few of them. And the hardest one is the print operator, to print to the screen or print to a stream. And that's just because it uses ostream, and but it's essentially the same kind of stuff. So let's go ahead and define multiply, and then we can go ahead and define something else. So I can say, okay, so it's or plus equals. No, we can't really do plus equals. So we'll use multiply. So what would operator multiply mean to me? And this is where it doesn't have to be circle on the left, circle on the right. We can kind of do whatever we want. I'm going to say, okay, multiply. What am I going to return? That's interesting, right? So maybe I'll just return a circle reference. And we'll have to see if it makes sense. But we have operator plus, and on the right-hand side, we'll have a double value. And we'll just call it whatever, the scale value, whatever that is. And so you can see we basically already done this with we're just changing up what goes on the left-hand side, what goes on the right-hand side. The left-hand side, again, is going to be an object of type circle. It's me, whatever me is. And the right-hand side is going to be a double value. And so, we're definitely changing things. There's no idea of const here when it comes to that. And so I can go ahead, and it really is a matter of just taking and just scaling the thing out. I'm just going to go ahead and just say, hey, my radius. Oh, hold on. This is a little different. So multiply versus multiply equals. In my head, I was doing multiply equals. So this does not modify. Can I put a const? Can I do it? Yes, I can. Because I'm not going to be modifying the object itself. I'm going to be returning a new temporary copy. And so I'm going to actually return by value. Because I don't want to return, because I'm going to create a value. I'm going to create a new object inside of this function. Uh-oh, what did I do? Oh, I gotta get rid of that. Right. Okay. So I'm going to be creating, realistically, all I'm going to do is I'm going to return a circle, and I'm going to say my x, my y, and I'm going to say the radius times scale. But I'm creating a brand new circle that I'm generating as basically a local variable inside of this function. And so I can't pass it by reference, because if I pass the reference to a local variable, as soon as the program keeps running, that thing's going to be just overridden by all sorts of stuff in the code, and it's not going to be right. And you might even get a compiler error if you tried to do this. So I'm returning a copy, so I'm going to be returning a value by return by value, and so I'm taking all my original values, I'm going to be multiplying it out so that everything works out the way the scaling works in this case. And so, a bit different. But now this is different than the idea of multiply equals. And so, like, what would I return? Like, can I put these things together? Can I chain multiply equals together? I don't know why I would ever want to. But in this case, it probably should be a reference, because I am modifying, because it's a multiply equals. I'm taking this and I'm going to be changing it to my own object here. So I can go ahead and define this over here. And this is a bit different here. I just say radius multiply equals by scale. And then I can return star this, like we were talking about earlier. Return myself after I've multiplied my radius by the scale. So the x and the y values stay the same, just like they do here. The radius is modified by this line of code, and then if I want to chain this together, I can, because I return this together. And so just to show that just to show what's going on here, we could do this kind of thing here. And we can do it for now. Let's see, d multiply, or let's see, I need two circles here. Circle D, circle E. And I can say E equals D times 3. And then I can say D multiply equals E. And you can see these are the two operators. Uh-oh. No operator equals matches this circle pointer and circle. So we'll fix that up in a minute. Let's worry about this one, the multiply here first. And so you'll see I can hit a breakpoint, I can go in there. So E equals D times 3. So let's say, what does that mean? It means we're going to take this and multiply this by 3, 12, so that, or just multiply D by 3, and it's going to set it equal to 12. So E is going to be 1, 1, 12 when this is all said and done. All right, so let's hit this line of code here. E equals D times 3, and we're going to see this is a little surprising here. So at the end of the day, E should be equal to D times 3, so it should be equal to 1, 1, 12. And it gets a little tricky here because you hit F11 to go into this, even though it doesn't look like I should be able to. I'm going to go into a function because, oops, I'm going into a function. Or am I not? What in the world? Run this again. F11, there we go. I don't know what's going on. And so the multiplier operator takes something and multiplies by 3. So x, well, let me go in first. So x is 1, y is 1, radius is 4. So this thing's going to return a 1, 1, 12. And so you're like, okay, the new circle is 1, 1, 12. And you're like, you mouse over E right now and you go, it's 1, 1, 4. And D is 1, 1, 4. And you're like, Brad, what is wrong with you? And I go, I agree with you, except for the fact that if I hit F11 one more time now, it now takes me into the equal operator. So I'm vindicated here. So now it will actually go ahead, print, and then set everything up the right way, so that when I finally kick out of this thing, now E is set to 1, 1, 12 and D is set to 1, 1, 4. So it did do the two operations as we were expecting it to do. And so that is, we've kind of shown at least that operator, and our copy assignment operator, and our operator here for our multiplication operator is working too. So now we just got to fix up, I'm going to fix this up and then get back to you here about the multiply equals. And I fixed everything up. So it just turns out that, as we were describing before, this multiplication requires a circle on the left-hand side, which is presumed by the function here, and the right-hand side has to be a double, and it returns a whole new circle, which then gets put into the whole idea of the copy assignment operator, because it just gets replaced in the so there's two separate operations. And so it's the same deal, but with multiply equals, left-hand side has to be a circle, and it is, and right-hand side has to be a double, and it is. And so now we should be able to kind of go ahead and do this and say, okay, now D coming in is, come on mouse, help us out, 1, 1, 4. So if we do this correctly, it should come out 1, 1, 20, correct? So I hit F11 and see I go into the multiply equals operator, and then I'm good to go. And now I'm multiplying out, my radius is now 20, I return star this, I'm not chaining this thing together anymore, but you can see now my D is 1, 1, 20. And it follows all the rules we had discussed about how we're scaling the radius, and that's all we're doing with this multiply equals operators. And so, as far as this is concerned, mine is going back in here and just getting rid of all the print statements. All of these operators are working pretty well, and they're pretty robust. We have to do some more testing on them, but for the most part, we're all good to go. And so, what other operators would there be? So we could have, let's say, coming back, let's just do this one more time now that I'm a little more secure on this, right? I could say, why don't I take a circle, and I'll say operator, and I'll say plus, and I'll take a const circle reference on the left-hand side, or on the right-hand side. And then, since we're here, let's do this for plus equals as well. Return a reference, plus versus plus equals, and then there we go. So one's a const, one's a not, right? So this needs to be a const, this not. So what I'm going to do then, if I do this together, I'm not going to add the radiuses together, but I'm just going to add the coordinates. And again, does this make any logical sense? It might not make any logical sense that I'm doing this, but part of it is just to show you that you can do this. So again, you don't force things. You don't jam a square peg into a round hole generally, right? You don't just make things work because you have to. So again, if this doesn't make any sense to you, then don't do it in the future. But just to show you how these different operators work. And so we're showing you now 2 of the 3 different ways, and we'll show you the third crazy one when we get to the operator overload for the print operator. That's the last thing we're going to do here. So this returns by value, this returns by reference. Let's define these things and go. Okay, so what did we do? Where did they go? They're over here now. Okay, so kind of coming back to it, it's helping me out. I want to return a new circle, and I go, okay, all I'm going to do is take my x value and add the other ones. And I'll take the y value and add the other one. And then I'll leave the radius. Or should I add the radiuses together? I don't know. It doesn't make any sense, I don't think. It doesn't make any sense what I'm doing anyway, right? So, but I'm adding the x and y coordinates together and leaving the radius alone. So I'm just moving something off of the position of another circle. Okay. That could be a video game related. It could just be if maybe you've collided with something and you need to move outside of that collision. So you just say, okay, I need to move over some distance. And so the same deal here goes. I just say Rx plus equals RHS dot x and y plus equals RHS dot y and return star this. So just like before, this sets everything up in one line of code with a new object getting returned, and that's why it's getting returned by value, because you can't return by reference a local variable or a local object. And then for this one, I'm modifying myself, and I'm just modifying the x and the y, leaving the radius alone, and then returning myself back if somehow you chain all of this together. And so that does it. So I can just by the same tokens here, I could just say E equals E plus D, and then I can say D plus equals E. I don't know, I'm just making, just to do stuff here. So let's take a look one last time. Here we go. So E is 1112, D is 1120, so it should move to E should be 2212 when this is done. So it does its work, and it comes back, and I got to set the equality here. And go, where am I? Up here. Sorry, I'm up there. Boom. Equal operator. And so now E is set to 2212. And I think that's what I was saying, because the radius was left alone, and the x and y positions were changed. And so going in here to the next line, the plus equals, well, D, 1120, and this is 2212, so this should come out as 3320 after this is all said and done as well. I'll go down here, and D is now 3320 as it's supposed to. So following the rules we said were going to work for these operators, the operators work exactly like they're supposed to. Okay, so we hit this line on the this. So let's talk about what this is officially, even though I have alluded to it, more than alluded to it a few times here. So it's a pointer. This is a pointer, and it points to me. Because when you call a member function, like any of this, or just even, let's see, D dot get area. How does when you pass along under the hood, the compiler actually also passes along a pointer or a memory address to D, so that it knows to use this function on that object. And so under the hood, it's passing along a pointer to D, and when you get into the getArea function, where is my getArea function, how does it know whose radius it is? Because it passed along that pointer. And so under the hood, and that's why in Java you see this all the time, you can put this arrow, we haven't discussed the arrow yet, but you can go ahead and do this. Once you say this, everything becomes this. And so you don't want to. Java kind of by default, people do this by putting this point, this dot in front of everything. But in C++, we generally do not do this. But this is implied that I'm talking about my object, this object's radius that I'm going to be using. So you say it's there, you just don't know about it until you need to use it. So at any point you're like, I need to return me, I use this. And if I need to return it by a pointer, I return this. And if I need, because of the syntax is involved, and if I need to return it by value or reference, I return it dereferenced using star this, and that's what you see down here. So this is saying it's always passed along, and it's always a hidden argument. In Python, it's not so hidden, right? If you've ever used Python object-oriented programming, you have to pass that thing along. It's just, there's no inference from it. You must explicitly call it to be able to use it. And so, again, so that this pointer is whatever I am, whenever I'm inside of a member function, this is me. And everything else has to be applied using like RHS or whatever, like in this case, RHS dot. That's how I know myself from the other object. Okay. So when it comes to these kind of operators here, you say operator equals, invoking, returning values. Oh my God, that is complicated. I guess, yeah, return star this. That's all it's saying is, if I, like with this, I'm chaining things together, and so when this thing returns, this first equals returns, it needs to return one of the two equals, and generally speaking, it should return the left-hand one. But when it comes to the function call, this is object 2, and RHS is object 3, so I should return myself. I should return myself so I can continue on forward. Okay, so again, coming back to this whole thought one more time, just to say, do any of these make any sense for a circle class? Maybe, maybe not, right? But we can change the meaning of an operator. Like if you really wanted to, you could change what multiply. Like I said, multiply could be anything, because I just went ahead and just said this is what it means. And so you have to watch out. Sanity, sanity should prevail. And so skeleton times skeleton, skeleton plus equals monster. What? What does this mean? So you probably don't need this in most cases. But especially for mathematical operations, yes, definitely something to use. So I cannot change the number of operands. So everything is two-sided. There's something on the left-hand side, something on the right-hand side. I can't redefine the fundamentals of what this operator does. I would have to create a function if I wanted to do something like that. And then it's not overloading the operator anymore. And only certain operators can be overloaded. There's 20 or 30. There's a ton of them. But you can't just make up your own. You can't just say, I don't know, you can't just say, ampersand this, just make this up. That means something. That will never be a thing. The compiler will never be able to handle that. It's too complex of a task to force the compiler to understand that you're making up your own operators. And it doesn't even make any sense, because if you're making up an operator, who else other than you knows what's going on with that operator? Okay, so other things, we'll see this in the future. We'll do this last one here, plus plus. Like plus plus minus minus, the square bracket one we can actually access something like an array. We can access an object like an array. We'll need that for vector. We'll need that for other things. And so again, coming back, you can overload a whole ton of them. And just remember, there's prefix versus postfix. So there's another rule you have to remember. How do you know which plus plus which function is actually which is the prefix overload and which is the postfix overload? And let's see, overloaded relational operators should return a bool. Relational operators, less than, equal, you should not change up the base behavior, especially if you're using the standard template library and that sort of thing. Again, we'll overload that later, and we'll talk about this at another time here. Let's see, in a second here, let's do the hardest one, and we'll do this operator for output string. So my end goal is to be able to do something like this. So I could do an std : cout, and then I can just put in e, and then maybe an end line. Something like this, right? We can't do this normally, and it's already screaming at me for D and E because no operator exists. So I have to define this for my class in order to use it. And so, again, once you've done it a few times, it looks really complicated, but it kind of follows the same kind of rules. And this is where we're coming back to the term friend from earlier. This is just the rules. It has to be a friend operator. I do need IOStream here. So if that's the case, maybe I can go back over to here and get rid of IOStream, because now I can include it here. So I'll get the same behavior since this includes this, which uses that. All right. So then now I can say I have a friend function. It's going to return an OStream reference, because I can chain, you know this, you can chain together the prints. I can do, arrow, arrow A, arrow, arrow B, arrow, arrow C. I already did it with an n-line character. So I can chain this thing together, and I should always return the stream every step of the way. And I say my operator is, the arrow, arrow, stream operator. The left-hand side is an OStream reference. Oh, sorry, it needs std::. So it needs to be std::, OStream. And isn't it fun? Look at the syntax, right? You're running right over to Python right now as I'm talking. So let's see. You could use the left-hand side for this. This is different in that it uses 2 parameters. Instead, all of these had 1 parameter, and the first one was presumed to be this object, me. But because this is a friend function, this is not a member function. This is halfway between global and member function. So because of this, the syntax is different. And now I say, this is the first parameter is presumed to be what will be on the left-hand side of the operator. And then whatever comes next, the second one, a const circle reference for RHS, that will be what is on the right-hand side of the operator. And so right now, that might fix up this, say, I'll get a linker error because I didn't define it, but at the very least here, that fixes up the error that comes up here. And this will compile, but not link. Because I have to now define this function for what this means for this thing to work. So I can do it just the same, and the hard work of this is out of the way because that is the most complicated one, the most complicated operator, overload. Returns a stream reference, takes a stream reference. It's not const because you're modifying it as you're adding to it. And then this kind of stuff here. So your job is to do as little as possible to print out this object. So I'm just going to print out, and you don't print out to cout, you print out to OStream, because this could be cout, this could be a file. There could be other things than just plain old console that you're spitting this thing out to. So I want to spit out a parenthesis. I want to spit out the x value. I want to spit out comma this, and then I want to spit out the y value. Then I want to put something like this with radius after it, with a colon, and then I want to print out the radius, and then I want to print out an n-line. And so this is screaming at me because I am not inside of a member function. I am inside of this class, inside of this function that doesn't. It's a friend function. So I can go ahead and say RHS dot, and I can say RHS dot and RHS dot. And this is the whole reason for the friend part of this, is that if this was not a friend function, if that function didn't say, hey, I trust you with circle. I trust this function with circle not to ruin anything, I couldn't access the X directly. I would have to call the get function or whatever it is I need to do to get that information. And in some classes, you're not allowed that information. So it would be impossible to do. But in this case, because I made it a friend, I'm allowed to access the public data. I'm sorry, the private data. And now because of all of that, I must return a value from here. So, and I have to return my stream. So I have to return oster. And now this should compile and run. And now let me get rid of this breakpoint here. And you can see now on the screen, there's everything I'm expecting. There's my 3.3 radius 20. There's my 2.2 radius 12. And with an n-line character. And so it printed out nice and compact and neat for me. And it printed out only what it needed to get the job done. All right. So that is, let's bring this back so you can see it in all its glory here. Whoops, almost. Can almost get it there. There we go. And so you can see, there we go. Oops, oh, shoot. That's the whole thing. And so the hardest part is just remembering this format. And it's different than all the other formats we've seen so far because it takes 2 parameters because it's not a true member function. It's a friend function here. The last major topic I wanted to cover in this video is something that's a little bit different than what the next video is going to be. So the next video is going to be polymorphism, inheritance, virtual functions. And so that takes what like the circle function and uses it as a template, and it advances it and makes it more custom without having to reuse code. So that is what, that is the powerfulness of this, and it requires pointers, and it requires a whole ton of information that we don't have here at the current moment. So just kind of say, wait for that. The whole other idea of programming here is what's called aggregation. And so I can actually show you an example of this because we have a nice working circle, and we can kind of make this thing work. So we'll talk about this next time. The idea of inheritance and polymorphism is what we call an is-a relationship. A banana is a fruit. A student is a maybe not a student. An undergraduate is a student. An athlete can be a student at COD. We do this all the time. We group up ideas, abstract ideas, physical ideas, so that we have them set up so that our brain can comprehend when we see it. We see something, we go, oh, that's a fruit or a vegetable or that's a door or whatever it is. That's just how our brains normally work. That's the is-a relationship. Fruit is a banana. But when it comes down to it, this lecture, this part is going to call aggregation. It means a class is a member of a class. You have a class inside a class. And so you can think of this as a has-a relationship. A car has a steering wheel. A car has seats. A car has tires. A car has radio. A radio has buttons. Radio has a CD player, maybe, depending on the year it is. So forth and so on. The CD player has. So it's a completely different relationship. This has a relationship versus an is-a relationship. And so we can see that we can make this thing work. And we can use the circle class to show that. They're using this idea here of a student contains the whole idea of what student info means. Because instead of, so it makes sense to break this thing down into smaller parts instead of just jamming out all the variables just, one after another. There's nothing stopping you from breaking this up into more manageable chunks and just say this student has student info that is part of it. And so to say that the UML gets a little more complicated, as you can see, because a course, for like a course that that you would take or I would teach, would have an instructor, and it would also have a textbook associated with it, and whatever else and notice every time I said that it has an instructor, it has a textbook, and in this case it would have a bunch of students. There's other things, it has grading, it has other things, and so this again is completely different than the next video that we would set up, and so. Just as a quick, let's just see about this idea. Well, what would I do to make this thing work if I wanted to take and think of like a cylinder class? And so a cylinder is not a circle. A sphere, and this is where the trickiness is a sphere a circle that's just rotated 3D? I don't remember enough about my solids of revolution. It's been 20 years now. But I do know that a cylinder is definitely not a circle. It uses a circle. And then it adds a height component, but it definitely is not by itself just that. It's and so I would have to say it has a circle. And so what I can do here is set up, let's just move this over, get rid of everything else, is set up a cylinder object here, new item, cylinder.h. Let's say, okay, I have class cylinder. I'm going to need, let me spell that in first. Okay, I'm going to need circle because I'm going to use it. Circle.h. Okay, and so under the hood, we can make this as complex or as simple as we want. But under the hood, the cylinder has a circle. I'll just call it C. And then it also, so circle the position, the XY position in space of the center of this thing, and let's just presume it's the center of the whole object. That makes sense from a video game standpoint for rotation and scaling and all sorts of stuff anyway. And so with a circle, that gets me the X position, the Y position, and the radius of the circle, and then the only thing I need to maintain on this end is the height, and that could just be a double. Okay? And so now, just to set things up, I need a constructor for my cylinder. And so I do need all the things before. I need an x value, I need a y value, I need a radius, and I need a height. Oops, counts. So I need 4 pieces of information now to make this thing work. And so now we can go ahead and I can set up the constructor in the CPP file. Yeah, save that. I want to drag this over a little bit so I can see both. Open this. There we go. And so now we can fill in the details as we need to. And I can go ahead and say, okay, what do I need to do? I need to fill in the circle first. So I can say C. And notice I can use that constructor. I can pass x along. I can pass y along. I can pass radius along. And this is a nice step into next week because we're going to do almost the same kind of deal with inheritance and polymorphism. It's just different conceptually. But when it comes to the syntax, we're kind of doing the same stuff. The circle maintains 3 of our 4 variables, so 3 of the 4 parameters should get those values. And then afterwards, I can say, well, my height is equal to the height of the other thing. Okay, and so there we go. And now we have this access, and it's done. The x, y, and radius is set up as part of the circle object, and the height is set up as part of the actual cylinder object. So it's like 2 separate objects are working together to maintain all the information I need. It's like I like to call it Frankenstein's monster because you can jam all different parts together and it just kind of works. Okay, so then when it comes down to it, the tricky part then comes when it comes down to the gets and the sets, because this is private, this circle, this is private data, and I don't have public access to all of the get functions and the set functions and everything under the hood. And that is kind of a consequence of this, is I've kind of privated away this. And you're like, why not make it public? Well, if I make it public, anyone could just go in and change any of those values. And generally speaking, that's not what you want. Maybe it is what you want, but for this kind of case, and so it just gets tricky. I'm not going to do it because I'm just showing you an example. I'll just do one to show you. If I wanted to do some kind of function that gets and sets the x value, I would have to define it over here on this end. And then I can go ahead and define them inside of this cylinder class. And then I can access private stuff. So I can say get me c.getX. And this is where things get complicated. And I can say c.setX, x. And so it takes 2 steps to get me there. I have to have a function in cylinder that goes into circle to do the actual work. And so I would need a function that does every part of that. And of course, I would need to define the new functions here as well. Let's not worry about that. Let's worry about that next time when we're talking about the area function, the volume function, the surface area, the circumference, all of these things. Let's worry about the next time for real when we can discuss using virtual functions, polymorphism, and inheritance. Okay, but that's just to say, this is a consequence of keeping this data private, is I have to double my workup and I have to supply wrapper functions that I'm going to allow the user to use. Okay, so that is all I want to cover for that. Okay, so I would be remiss to avoid talking about all of the new standards that are part of things that are 9 years old at this point, the 2011 C++ standard. When it comes to this idea of R-value references, move semantics, what is all this crazy nonsense? And again, most times you don't need to use these things. You don't always need to use a copy constructor or a copy assignment operator, or you need to overload these operators. But when you do, you need to know how to make them work. And the same goes with this move semantic. And so the whole point, as I say, a big problem of C++ is that you write your code and you're none the wiser, right? But you're making so many temporary copies of objects and just values. And they're just getting copied and passed along, then another copy is made, and so forth and so on. Your computer is spending so much time making copies of things sometimes wouldn't you like it to do real work? And so C++ in 2011 changed everything up to make this a lot more accommodated for the fact that we can eliminate some of these copies if we're smart about it. And so consider something like this. If I have int x equals 2 times 6, well, the compiler takes 2 times 6, creates a 12 somewhere in memory, and then stores that as a temporary value, then gets stored in x, and then the temporary goes away. There's a lot going on just for one simple line of code. You would like to hope that that's stored on a register to make your life easier, but you don't know. You don't know if that's stored in a variable. You have no idea what's going on under the hood. And so consider this kind of stuff too, for just calling a function to get work out of it. Okay, so in this case, I'm calling the square function, and so I'm passing the 5 along. So this is more assembly language. What is actually going on? A 5 gets pushed onto the call stack. The function gets called, and so the function calculates 5 times 5, 25. The 25 gets put onto the stack. The temporary value is copied, so it's creating a temporary variable, and then it's maintaining that, and then it's passing along, and then it's making another copy to pass back the value that is the true value to return. So it's like the temporary value is no longer needed, so this 25 falls away, but this copy of 25 is what's pushed forward and then presented as the result of the function. And it's complicated just trying to describe it. It's complicated. Just think about all that extra work, and that's, like, this is just for something as simple as what you see in front of me here. And so, listen, there are 2 types of values stored in memory during the program, the execution of a program. There's values that persist beyond the statement that created them, and then those are L values, basically left-hand side values, L value for left values, and that is pretty much associated with things that have a memory address. So like in our case here, D has a memory address. E, like when we're looking at these lines of code, D and E have memory addresses. But when you think about it, what is this doing? This is multiplying D times 3, returning a temporary, remember, returning a copy of a new object, and then that object's getting copied in, and then the temporary is getting destroyed. And so this is what we call an R value, because it's creating a new temporary object that doesn't have a true memory address because it's only temporary. Once its job is up, it just gets thrown in the trash and thrown away, and so it's an R value. And so we can discuss all of this kind of stuff, and again, this is not the time and place for this. If you are very interested in this, look up the Jesutis book that is part of the second edition C++ STL Jesutis book. Look this up in many other places, because right now, just to say the circle class doesn't need these. And just like we were talking about, why do I need the copy constructor? Why do I need the copy assignment operator? It comes down to our future here in this course and in your future in programming, and when it comes down to using pointers and newing up memory and making sure if I copy values from one place to another, that I'm making copies of all the data, not just copies of pointers, so that 2 things are pointing to the same memory address. If I want to copy a vector, I want to make sure both vectors have copies of the same data, as opposed to 2 things pointing to the same data, and if I change it in one, it affects both pointers. And so that's where it all comes down to. All this pointer and reference nonsense is why we need all this extra complexity and why we need these R values, because I can speed things up. If I'm making copies and copies and copies, and I can pass along and say, instead of making a copy of all of this data, since it's just a temporary anyway, how about I pass that pointer along to all that data that I generated, all the memory, whatever I generated, so I don't have to copy it more than one time. Make it once, and then I can just pass the pointer along. Just like, think about how we're passing when we pass into a function. We pass by value, which makes a copy. That's essentially an L value. Or we can pass by, well, they're all L values. But we can pass by value, which is a copy, or we can pass by reference or pointer, which passes a memory address. And that's essentially what we're doing here. We can pass along a copy of data, maybe because we have to for regular data, but if there's ever a chance, we're going to go ahead and pass along the real data because the temporary has already used it, and it doesn't need it once it's done its job. So that's, all of these slides shows exactly that stuff. And I went ahead and I showed you, and the syntax is crazy because the ampersand gets another, because you can use ampersand for bitwise and, you can use ampersand for address of, you can use ampersand for bitwise and whatever, and you can use double ampersand now for move semantics, and you can also use it for like dual conditional statements inside of an if or a while or things like that. So there's a ton of uses for this little tiny ampersand. And so to understand the move semantics, you use double ampersand. That's like the new syntax. And so the move constructor looks very similar to the copy constructor. It's not a const because there's technically a way we can technically change. I'm not going to get into the details. We can remove and eliminate these pointers and set them equal to 0 and null pointer. So we can actually change things as we're copying from right to left, from temporary to not. So the move constructor is not going to be const, and the same goes for the move assignment operator. Even though it takes in using the move semantics, it returns using the reference semantics. Isn't that crazy? Isn't that weird? But that is the syntax for that kind of stuff. And then now there's no difference between what you see here. I wonder what's going on here. But anyway, there's no difference between what I wrote here and what I wrote for this. Like you can compare this to that. It's exactly the same code. Because for regular normal values, we don't have to do extra work. It's only for dynamic memory that we're kind of shifting along from right to left that we would have to set these pointers to null so that when the temporary gets destroyed, it doesn't destroy the memory. It destroys null pointer, which is fine. And again, this is maybe a future problem depending on your experience level. But this is a pretty cool new thing to speed up your program extensively. So coming back, when I run this program now, the one we had before, and I incorporated this, I did not change any of the code here. But now, it actually calls the move copy assignment twice. Before, it used the copy assignment operator, and because we defined our own move, I'm sorry, let me make sure I said this right. That we were using the regular old copy assignment operator a minute ago, but now that we define this move copy assignment operator, it's using that instead. And so I can show you here. And that's because, again, this is creating a temporary, an R value that's going to be used to copy into an L value. And so I can go ahead and see where is this? Yep, here it is. Oh, I'm going to return multiply. I'm coming back out of, I'm going into here, and now it's in the move copy assignment operator passing along by move semantics to do the job. And again, at the end of the day, it's doing the exact same thing. All of these different ways to do the exact same stupid thing, but in C++ it all matters because that's how the mechanisms apply to the language here. And so I don't have the move assignment or the move the move constructor. I don't have that ready for you. But just this is the whole point. Just describe this idea, and as you move forward, it'd be cool if you could try to implement this. But I'm not going to force this on anybody, as I'm learning this myself because it's newish. And it's not, it's one of those things we don't hardly ever use this down here at the education level at the first and second year. I don't know, since I haven't been in the field for a while. Don't know how much this gets used out in the real world, but I can imagine quite a bit, especially for programs that you want to crunch down and make your programs run as efficiently as possible. Gaming, especially. I should get on this if I'm supposed to be a gamer. So that covers this lecture. I'm appreciative for you guys following through with this and sticking through the whole video. So we've covered everything there is to know about object-oriented programming except for inheritance polymorphism and virtual functions. That will come next. So as always, swardb@cud.edu is a great way to get a hold of me. YouTube comments, a great way to get a hold of me. Never sit on your questions. Always ask away. Don't be apologetic, especially students. This is your time. You're paying for access to answers to these questions. I will give it to you as quick as I can get them. And otherwise, moving on to Chapter 15 next. Thanks, everybody. Have a great day.